thank you all for coming to this portion of the symposium presentation. I'd like to start off showing Dr. Eric Drexler's video at a TEDx conference. He's discussing future of radical abundance, transforming the material basis of civilization. It is a presentation on nanotechnology and how it will influence the future. After we're done watching that, I'd like to show a little presentation to start a discussion on the topics that were covered in his presentation. So with that said, I'll go ahead and start the TEDx presentation.
Good morning. I'd like to thank the organizers of this TEDx event and the United States Embassy in Lisbon for making it possible for me to be here today and to talk with you about what I expect will be some of the most important developments of the 21st century. The topic is as large as the civilization itself, in some sense, the material foundations of our civilization. And by that I mean all of the manufactured things that are around us. We're in a built environment. Virtually everything that you can see here was made with the aid of machines. It's a product of the Industrial Revolution. The prospect ahead of us is for a revolution at the foundations of our material civilization, a revolution coming out of a new kind of nanotechnology. Now, the greatest and most important kind of nanotechnology today is the one that we're using right now. It's the nanoelectronic technology that has made possible the information revolution. The technology of computers, telecommunications, is based on nanoscale devices, billions of them on chips, working together at high frequency to process and organize patterns of bits. The prospect ahead of atomically precise manufacturing is somewhat parallel, but with nanoscale machinery in place of nanoscale electronics, and organizing matter by processing molecules and organizing patterns of atoms. So this has parallels, and yet it is fundamentally different. It's a technology for the future. What makes this prospect important is that it will provide a way to solve urgent global problems on the scale of climate change and the grand collision between our industrial civilization and the limits of Earth. Throughout human existence, the nature of our societies and lives has been determined, largely defined by our tools. The Stone Age, of course, used stone tools, and growing out of that technology over a period of many thousands of years came the technologies of metalworking. People learned to smelt iron, to build iron tools, to hammer the metal, blacksmiths, using tools to shape the iron products of daily life, but also to shape better tools, tools used in the next generation to build yet better tools, in an unbroken chain of advances in fabrication, in manufacturing, that led to the Industrial Revolution, based on shaping pieces of metal with greater precision, steel, and making systems of machinery that brought a revolution in not only the quality of products, but the scale and cost of their production. And that revolution carried us very far. People eventually learned to shape metal into the rocket engines that took our civilization to the moon. And doing so brought a new perspective to the world. The environmental movement was largely launched by these images of the Earth as a finite, closed system. And I came of age during the time of the environmental movement. I had a very small participation in the first Earth Day. And when I went to MIT, it was with the aim of trying to address this problem, this collision of industrial civilization with limits to growth. And so I studied space systems engineering as one way of looking beyond these limits and constraints. And there I joined a community of people who taught me something very important, which is how to dream bold, audacious visions and make them concrete and detailed and quantified, to look at what can be done by thousands of people with billions of dollars over perhaps decades, and produce concrete results that are subject to quantitative analysis where people can check the numbers. And so that perspective is one that I found myself turning to the molecular world, because during the 1970s, people in the molecular sciences were learning how biology works. And what they found at the bottom was a manufacturing process, the first of the molecular, atomically precise manufacturing processes that I'll mention, which is the material basis of life, which centers on genetic information, digital information being used to drive a manufacturing system, a productive piece of machinery. So what is happening in all of your cells right now is that genetic information is being transcribed into the same information in RNA, which is being fed through a machine called a ribosome, which puts together, see the strand coming out the top, the red strand, puts together amino acids, atomically precise building blocks, puts those together to make atomically precise chains, the chains of amino acids that then fold up to make protein molecules. Now, when I began to study this, I asked the question, what can we build with these tools? And soon concluded that it should be possible, would be possible, to learn to design and fabricate materials made of protein that hadn't been seen before. I published the first paper in this area, the one that founded the now burgeoning field of protein engineering. And when I speak of using these tools to move forward to build better tools, much as blacksmiths built better tools to move toward the Industrial Revolution, it's important to recognize what protein is. And when I say protein, people think of meat. Meat is mostly water. Instead, I would like you to think not of meat, but of horn. And horn is an engineering material. It has properties like wood, like polycarbonate, and it's important to keep in mind if you ever find yourself in a field with one of these animals that it's a weapons-grade biomaterial. Many people have discovered that to their a major decrease in their health, shall we say. Now, in addition to being a hard material for weapons, it's an engineering material. As craftsmen, master craftsmen in Russia demonstrated in the 19th century, one can build something as intricate and precise as a pocket watch from wood, one similar biomaterial. And as with blacksmithing and progress toward the Industrial Revolution, the direction of progress once again will be toward greater control, better materials, the ability to make better devices and better machines, using tools to build better tools and to put parts together. Now, what one finds, what I discovered in investigating this area, is that the kinds of components that are used to make machines in the macroscopic world today almost always have potential counterparts in the nanoscale world. That devices like planetary gears, same function, can be built where the gear teeth are rows of atoms rather than pieces of steel. Differential gears, the same behavior, the same motion, the same function. And gear systems. Those are examples. They include drive shafts. They would be connected to nanoscale motors, bearings to allow the motion. And with these components, mechanical engineers know that they can build complex systems, including the kinds of systems that are used in manufacturing. And so this opens the door to manufacturing in the molecular world in a style that's very different from what we see in biology. So, in factories today, you find moving parts, taking components, bringing them together to assemble larger structures. And if you looked more closely at these machines, you would find gears and bearings and shafts and motors and conveyor belts. And all of those machines that execute these patterns of motion to bring parts together. Form follows function. Motion paths to bring parts together are similar on the nanoscale and macro scale. The analogies are direct, very concrete. And so, with these technologies, when we have the tools to build them, one can build manufacturing systems on this scale. And here's an illustration of the kind of thing that can be built. You can see here nanoscale machine parts bringing atomically precise components together, small molecules, transforming them, and placing here pairs of carbon atoms together to make, in this instance, diamond, which turns out to be an excellent engineering material. I should note a little background reading for scientists. This area of study is at the juncture between the molecular sciences and mechanical engineering. And mechanical engineers, by and large, do not understand the molecular sciences. And molecular scientists, by and large, don't understand mechanical engineering. And as a result, ideas have fallen through the cracks. There's been enormous confusion. Mythologies have developed, and there is a need for a much better grounded discussion. So I urge scientists in the audience to download Drexler's MIT dissertation, search and download, if you want to read about the quantum chemistry, the thermal fluctuations, the components, dynamics, and system architectures of these kinds of systems. So that addresses atomic precision. High throughput, scaling laws are crucial to that. You can see in nature how scaling laws work. Large birds flap their wings about twice per second. They're on a meter scale, factor of 10 down in size, 10 times the frequency, and so on. And extrapolated down to a 1 micron scale, you get rates of operation of 2 megahertz in this example. So it turns out that if you go through the exercise of designing these machines, you can measure the size, and the sizes are smaller by roughly a factor of 1 million. And so the scaling factor of frequency in this instance is a factor of 1 million. And what that means for manufacturing is enormous. When you get a factor of 1 million change in a parameter in engineering systems, you open a new world. It's fundamental. It's like the difference between a chemical explosion, a nuclear explosion, the difference between having a rocket that goes up into the air and falls back, and one that travels out of the solar system on a journey of decades. A factor of 1 million in speed means 1 million times more components per second per individual machine. Per ton of machine, it means 1 million times as much mass throughput. If a macroscopic machine can make process 1,000 tons of material in a year, analogous nanoscale machines could process 1 billion. And that is where the potential for world-scale change comes from in this technology. So I've spoken of putting pieces together to make larger pieces. Here is something, again, like the components you see in factories. This animation was actually done by a mechanical engineer. What you saw there are small blocks being put together to make larger blocks. Now, spanning the gap between the nanoscale world and the macroscale world can be remarkably direct. Taking small building blocks, they can be put together in parallel by many machines working together to make larger and larger structures. And the scaling law for this kind of assembly is one in which, let's see, that example showed 4 assembly steps putting together 16 pieces. Take that forward, and one finds that 30 steps put together 1 billion. Of course, the purpose isn't to put together little tiles, but to put together intricate 3-dimensional objects, which might be made of superior materials, denser computational systems, putting blocks together to make larger blocks, which ultimately can be assembled into more familiar macroscopic systems. Now, if that block, the cubic centimeter scale, were a system built with atomic precision, it could hold 1 billion processor cores, 10 billion gigabytes of information storage, far beyond anything that Moore's law of progress promises. Building up with atomic precision from the bottom is a very powerful approach to improving technology. So I've addressed high throughput, comes from scaling laws. Atomic precision comes from starting with nature's atomically precise molecules and putting them together while not losing that precision. Atomic precision leads to new materials. Structure of matter can be controlled much more thoroughly. New materials leads to new components and to new systems. From this comes an unprecedented scope of production, the range of things that can be made, broader than what's found in industrial civilization, increases in scale of production, and reductions in cost. Billion-fold improvements in information technology, 10 to 100-fold improvements from better materials in aerospace, and even in mundane areas such as housing, lower cost, higher strength, higher efficiency, immunity to earthquakes, tornadoes, hurricanes, production on a scale that could bring a very high standard of living to people around the world. Now, what makes a change in our industrial technology base very urgent today, and this illustrates the notion that these systems resemble printers, digital information in, complex products out. What makes it very urgent today is that there's a need to transform our energy supplies quickly to move away from carbon to renewable sources like photovoltaics, and to deal with the increasing CO2 problem, which is changing climate rather rapidly. Levels increase despite international agreements and efforts to change technology and so on. They're expected to continue to rise. And to have the 21st century have a planet that resembles what we've had in the previous human history will require taking the CO2 levels down, and that is an enormous project. One can calculate the energy required. It's huge. The area of photovoltaics required to generate that energy is enormous. The costs are out of range of what can be handled by the world today. But the prospects with a better means of making things, more efficient, more capable, are to be able to do a project of that scale at low cost, taking molecular devices, removing molecules from the atmosphere, photovoltaics produced at low cost to power those machines, can draw down CO2 and fix the greenhouse gas problem in a moderate length of time once we pass the threshold of having those technologies. And that is a matter of using tools to build better tools. We've gotten this far to the scale of the Industrial Revolution. We now have in hand tools for beginning to build with atomic precision, and we can see pathways from there to a truly transformative technology. So the future today increasingly looks, as many people feel, rather bleak. Running in the collision between our industrial civilization and the limits to Earth is becoming more urgent. Many people look forward and they don't really see a future. But now we can see a path that leads to a very profound change in how our civilization works, how it interacts with the world, one that can make a different 21st century. And so I think that in our homes, in our businesses, and internationally, it's time to begin to change our conversation about the future, to consider prospects that are very different, prospects that offer a new kind of hope for the future of our civilization. Thank you.
Okay, so what did you think about the presentation? Did you find out anything you hadn't already known about nanotechnology, or do you know what technology is? Or did you find out anything more about it? Anybody? What is nanotechnology? Things on the scale of 10 to the negative ninth? Okay. That's usually the answer. what I want to speak about is some of the things that he talked about in his presentation, and then expounding upon it. A little more elaboration on some of the things he talked about. We need to start talking differently about nanotechnology, because when you bring up the term nanotechnology, you get a resounding thud, because no one really knows what's involved with it. Or they just go starry-eyed and go, well, it's really high technology stuff. Well, it is high technology stuff, but it's not like we don't know how to do this already, as Dr. Drexler has said. We've been manufacturing things since man started walking upright. And so I'm going to discuss the things that we do know and show you some of the problems that are involved that we can bridge to get to the point where we are doing something called absolute precision manufacturing. And that would be at the atomic scale. And so these are the terminology that we need to start using in our vernacular. Rather than talking about nanotechnology, we need to talk about being absolute in precision, and we're talking about at the angstrom level. So extremely small. Okay? Drexler says that nanotechnology is organizing matter by processing molecules and organizing patterns of atoms. He also says that this technology is for the future. It provides a way to solve urgent global problems, climate change, energy, and the limits of mankind upon its Earth. And he's probably right, if we can get to that. I think we can get to that, and so I'll demonstrate some of the things that we know that can get us to that. So, the technology management paradigm, and I would call this a manufacturing systems paradigm, since that's my background. We know how to do this. We know how to manufacture things and get to the point where we can get anything we want in about a day's notice. Back in the day when I was a kid, you couldn't get certain vegetables out of season. Now, if you want strawberries, you can more or less get strawberries within 24-hour notice in your local Walmart or whatever store there is. So we have developed the supply chain. We have developed all the technologies that allow us to have that supply chain, and that has a major impact on our ability to get to the point of absolute precision manufacturing. So here's the process that we already know about. First of all, we come up with the idea. When mankind was in its infancy, the first thoughts were, okay, I need to survive, and so I will develop things that will help me to survive. So the idea came out of toil. Life was hard, so they developed tools to make their life easier, or it was based upon survival. So next thing that occurred was identification of materials to use. If it was close by, picked up the material and you used it for whatever reason, whether it was a rock, a shell, grass, tree. Sometimes it was good, sometimes it was not good, so there was a continual looking for a better material to use. Then there was the manipulation of that raw material into a simple tool. Well, the basis of our tools, we know, are the 6 simple machines. I would throw in a couple other ones, but these are the ones that are established. So we have the lever, the wheel and axle, inclined plane, the wedge, the screw, the pulley. I would also put gear on there. And then also mechanical and after the mechanical, I would say there is the chemical and the electrical. For instance, he was talking about the manipulation of iron. Well, that involved a chemical process, which was smelting, as we all know. After that, the next step was the use and development of technique of those tools based upon the materials that we used. And then it was a refinement. And the refinement involved with constantly measuring how well it was used. We made it so it was in proximity or with the ratio with humans' abilities to lift things and use things. Repeatability was the next thing. We wanted to, if we used a tool, we wanted to make sure we could use it for the same application over and over again. Then there became standardization. That was standardization of use and standardization of that is the tool that we are going to use for that job. There was also classification. As we developed tools, we had tools for specific applications, then we incorporated those tools for other applications, and then we had tools that came together to make larger tools. After that, there was the refinement of the technique of these tools. So we could call that simple tool based upon those original 6 tools a subsystem. As we are developing as we have developed a subsystem, the next thing that happens is somebody is coming along with this exact same process and they're making up another tool. So as other subsystems, not just singular, so we're not just talking in 1 or 2 subsystems of tools, we're talking about multiple systems of tools. For instance, Model T. If you look at the Model T Ford from 115 years ago, 100 years ago, it is about the same technology as a go-kart today. If you were to open up a hybrid vehicle, there are many, many subsystems that are much smaller than they were compared to when the Model T Ford was developed. So they come together, then we have a system. After the system, because of all this path that we've gone from developing of the idea to material to the tool, we're developing lots and lots of information to keep making that tool and passing that tool knowledge on. After that, we have the development of system technology. Things start out, they're clunky, and then they go to more refined. For instance, the Model T to, say, a hybrid car today. From clunky, it goes from big to small, and that's where we're at the process now with nanotechnology. We run into aspects of economic justification. In other words, if you make it, we're developing it for value, other people want to use it. And then we run into issues of developing it for economy of scale and economy of scope. We're searching out new markets for our use, and then I have at the bottom wash, rinse, and repeat. So this has been going on for hundreds, if not thousands of years. And so that's our manufacturing technology management paradigm. Okay? Here's some of the problems, and this is getting to the more or less the gist of what Drexler was talking about. Alan Rowan, I picked this just because it would fit in the time frame of the symposium. There are a whole lot of other presentation that Drexler's done, and he sparked a lot of debate. A lot of people say, yeah, this is really good, but what type of time frame are you talking about? Do you think we can do this in the next 10 years, or is this a generational thing, or is this 2-generation things? And so some of the things that have come up in these conversations is, what are the impediments to getting to this nanotechnology / absolute precision manufacturing? Well, there's the human element. Most people don't realize that Drexler's talking about things that are really good, that they can impact and help mankind. But as he talked about in his presentation, there is the scientists at one end, and there are for research purposes, and as I categorize research, if we knew what we were doing, it wouldn't be called research. So it is finding knowledge using set standards and set principles to find things out, to enlarge knowledge. Then we have our engineers that do the applied research. And as I have on here, Houston, we have a problem for, well, what was it, Apollo 13, that the research done on engineering terms is to solve problems, solve technical problems, or problems that already exist with things that we already have. So we have to find a happy medium and get the scientists and engineers to start talking, getting together and having a common language or common knowledge. There was also the issue of that as we develop more technology, mankind becomes out of balance. The last time that society was really in balance, and I'm talking in terms of economically, so rich versus poor, ecologically, sociologically, world population, was about 1750 before the Industrial Revolution. Okay? So as we develop more technologies and we get more technologically developed, we also skew the balance in nature. And so the next thing is we have the science that's involved with it. One of the big things that we have to overcome is the ability to see what is going on at the nano level. Also, we have to overcome things like Brownian motion. I won't go into the specifics of that, but that's a big concern in terms of when you're dealing with one atom at a time, whether it's an electron or what have you. Okay, we know the process. Here are some things that people in society, or we in society, need to be looking out for just in general. And this would be the discussion between the scientists and the engineers. So quantum computing, that's going to be a next big jump, because that is the ability to process volumes and volumes of information that we've never been able to do before. Carbon nanotube development. In terms of DNA sequencing, most people don't realize that recently sequencing was done, or genetic material, 3 people were gathered to make in essence, to make another human being. People don't realize the impact that will have on society in years to come. 3D printing, that is a big thing that is coming, whereas literally anybody can, in their basement, garage, what have you, have the ability to make small size tools whenever they want to. Next thing is called NEMS, and that would be nano electromechanical systems. Next thing to start looking for is a refinement of covalent bonding. Think in terms of plastics, because many plastics are truly the manipulation of the building blocks of life, whether it's carbon, hydrogen, oxygen, or nitrogen. Also, scanning, tunneling microscopy, and then electron beam lithography. Now, a lot of people don't realize at the university level, a lot of people have scanning electron microscopes. It doesn't take all that much, about $100,000, slight manipulation, and so some of the things that he was talking about, and one of the things that is really pushing nanotechnology or absolutely precise manufacturing is the ability to knock off hydrogens, knock off electrons on the structure of some type of material. And so that's what's going on right now, and we're talking about getting to the less than 1 angstrom or 1 angstrom level. So with that said, Drexler, I think he's on the right track, but there's a lot of work that has to be done, and part of the issue of getting to the point where developing this nanotechnology would be to start the conversation with people. So with that said, thank you very much for coming.